Well, good morning, everyone. Good morning, good afternoon, or evening, depending on where you're located. I know we are all spread out all over the world, actually. So welcome to our panel discussion. I understand we're following the NASA administrator. It's always a tough time slot to be in. I hope some of you stuck around to hear this discussion. It is going to be a good one. The topic today we're dealing with is Making It on Mars. It's an interesting title. I had a joke about that, but I thought better of it. But it does remind me of that song, New York, New York. You know, if I can make it there, I can make it anywhere. Once we've proven out some of these technologies, we might need some clever individual to parody that song for us. So, but today our topic is all about 3D printing, advanced manufacturing, and assembly capabilities for the future. My name is Trudy Kortes. I am the Director of Technology Demonstrations in NASA's Space Technology Mission Directorate. NASA is working to send the first humans to Mars as early as the 2030s. And just as we'll do at the moon, we'll need to build up capabilities and experience at Mars over time. As part of the Artemis program, in fact, NASA will increase infrastructure and capabilities to explore farther away from Earth for longer periods of time. Recently, we have seen some initial success of these of similar types of efforts with the successful Perseverance mission. The rover that's on Mars now is conducting multiple investigations that will support future crewed missions, including a key project by the Technology Demonstrations program that I run and I'm very proud of, which is producing oxygen from the Martian atmosphere. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, has demonstrated the capability to produce oxygen from the carbon dioxide environment of Mars. Scaled up, that technology could support long duration human missions there without the need to transport significant quantities of oxygen for breathing air or for propellant. So it's a really great first step for us in what we call ISRU, or in situ resource utilization technologies. You know, another needed aspect of the same theme is advanced manufacturing technology, advancements that will provide many needed elements in the sustainability of human presence on the red planet. So another large portion of my portfolio, about half, I'd say, of a significant amount of the program that I run, is dedicated to on-orbit servicing, assembly, and manufacturing techniques, technologies, and processes that will have significant impact once that full suite of capability is proven out, and which directly translates to our topic today. So speaking of that topic, with us to share some of the latest and greatest in technology advancements in this area are Richard Boling. Rich is the Vice President of Techshot. Josh Brost. Josh is with Relativity Space, and he is the Vice President of Business Development for Relativity. Pascal Rosenfeld for Aleph Farms, and he is their Director of New Ventures and Space. And then Justin Kugler. Justin is with Redwire, and he's their General Manager of Mission Solutions. So an impressive panel for you today to discuss this topic. So I'm going to ask now each panelist to give some opening remarks, some introductory comments about their company and the related technologies we're talking about today. So Rich, if we could start with you, please.
Sure, thanks, Trudy. And if we can go to my slides, please. You know, this is the first time I've spoken at this event, and so if I could be allowed a couple of minutes to tell you a little bit about Techshot. I think most of our other distinguished panelists are maybe even better known than we are, so a little primer might be in order at first. The next slide, please. These are the main focus areas for the company. We're an in-space research and manufacturing solutions company, and we focus on enabling biological and physical science research in space wherever there is, whatever platforms are available, whether it's ISS, Dragon, Cygnus, hopefully soon the Gateway, and even the lunar surface. And then in-space manufacturing is a key focus for us, again, at some of those same locations. And then just providing equipment and services that enable deep space exploration. Right now, focusing on the highlight of there is of that is some work we're doing on the exploration pressure garment. Next slide, please. Our headquarters is in Metro Louisville, Kentucky, just on the north side there in Indiana, where most of our folks are. And then we have an office and a lab at the Kennedy Space Center at the Space Life Sciences Lab. About 50 folks in total. Almost everyone is an engineer, scientist, or technician, and space is 100% of the business. Next slide. And we've been doing this for 30 years, a little more than 30 years now, and you're just seeing a few great past images where we've flown aboard the shuttle, we've done suborbital rockets, and flown aboard the Cygnus. We even conducted some research on board the Cargo Dragon before it docked on this last mission, and then we've been aboard the ISS since 2014. Next slide. We are a one-stop shop. You hear that a lot, but we're very vertically integrated. We do everything for our customers. We provide the equipment, help design the experiment itself. With our agreements with NASA, we provide even the launch and the recovery. We do the design our own circuit boards, build them, software, firmware, prototyping, manufacturing, and the integration of the final product after it's over, after it's built, and on-orbit operation as well. Next slide, please. Which we do at our Payload Operations Control Center, our little mini mission control, where we talk directly to the spaceflight crew who are conducting the research or the manufacturing for us. And we also operate our equipment remotely from our POC as well. Next slide, please. And one more, please. Our customers come from industry, academia, NASA itself. Essentially, you could consider that we're providing the picks and shovels that these researchers are using to make new discoveries in the life and physical sciences. And you can just see a few examples of different research areas that we provide these tools for. And many of them are being used now by our customers to help enable deep space exploration, help enable us to get to Mars in a healthy fashion and thrive once we get there. Next slide, please. Just a few of our payloads. We'll talk about more of these in just a sec. And again, our first payload launched to station after having been on shuttle for years on SpaceX CRS-4. And Justin, I think that was the first flight of the first made in space payload as well. So it's been great getting to know the made in space and now Redwire folks from way back in the day, and we've certainly followed their work with admiration and respect since then. Next slide, please. Couple of quick examples. So right now aboard the station, we have this X-ray machine from ICE. It's a DEXA scanner. You can see some of the companies and universities that have had us do research in space for them. And again, these are conducting bone research studies, muscle wasting studies to help us thrive in a fractional gravity or a zero gravity environment. Next slide. Advanced Space Experiment Processor. It's sort of a generic box. Next slide, please. We have 5 of them. Here it is being installed aboard the station recently. Next slide. You can see just how the cassettes work. The payload, the locker is kind of generic, and then we launch these laboratories in a cassette, if you will, and the crew pops them in and out at different times, and we control them from the ground. Next slide, please. Recently, an investigator, Dr. Jamie Foster at the University of Florida, had us send up 128 squid for her and for her lab, looking at host bacteria relationships, and really with an eye toward long distance trips to Mars, and just studying what we might need to do to keep those gut bugs alive and healthy and happy in those long distance crew members. Next slide, please. The multi-use variable gravity platform. This is a way to do fractional studies aboard the ISS. So we know zero G can be harmful, but is the gravity of the moon or Mars for a long-term occupation going to be healthy for us? And so we send up a lot of different sample types for our customers and do research by spinning these carousels at fractional gravity at 0.38 Gs. Next slide. And just a few examples of the different modules we've developed. We've even solidified cement at Mars gravity aboard the station. Next slide, please. We get the most attention, I guess, for this. This is our bioprinter. It's flown aboard the station. It's back here in our lab now, getting some improvements to improve throughput and print quality, and that's heading back up aboard a Cygnus vehicle next summer. It's really built to make 3D thick tissue in space. Next slide, please. Also have developed some vascular grafts, which go along with thick tissue. Next slide, please. We're working on plant growth chambers, which you'll need on the way to Mars and at Mars, and we partnered with Tupperware in the development of these. Next slide, please. We didn't build it, but we managed the science going on in the Advanced Plant Habitat aboard the station through the REMIS contract. Next slide. Same thing with research furnaces aboard the station that we didn't build, but we managed the science in them aboard the station through REMIS. Next slide. One more, please. So the bioprinter, absolutely, we intend to use to make organs and tissues eventually, not tomorrow. We've got a way to go, but we're at work on it now. And we've entered the deep space food challenge because we think we can bioprint your favorite In-N-Out burger or whatever your favorite chain is, or Wagyu beef or whatever on the way to Mars or on the surface of the Mars. Next slide, please. Working on something called the cell factory to make billions of cells in space to feed into that bioprinter. Next slide. Also, something called the pharmaceutical in-space laboratory to make drugs that have longer shelf lives in space, something that you're going to need on a long trip to Mars. Next slide. Fab Lab is a 3D metal printer, the biggest thing we've ever built. It makes aerospace grade metals, metal parts, and electronics. Next slide. One more. Keep going. So we've also built a planetary environment simulator here at Techshot that reproduces essentially every condition on Mars with the exception of the fractional gravity and the exact radiation environment. But the solar spectrum, the temperature, the atmospheric pressure, and the gas composition, and it's available for use. Next slide. I mentioned the exploration pressure garment, and that's also something that will absolutely be used aboard the surface of the Moon and Mars. Next slide. How we do all this? Again, we've got a Space Act agreement with NASA. We have an IDIQ contract with NASA, which speeds up contracting. The Research, Engineering, and Mission Integration Services contract with NASA helps us manage NASA equipment that we didn't build. And then, like others on this call, we have this Master Implementation Partner contract with the ISS U.S. National Lab, which gives us this guaranteed allotment of up and down mass and crew time. Next slide. So sorry, that's kind of a whirlwind tour of Techshot, but I think it's important to kind of show our depth and breadth. And really the takeaway here is that there are companies working on these enabling technologies that it's going to take to get us on the way to Mars and then to operate successfully on the surface of Mars. Not everything is ready today, but hopefully there'll be a convergence when it needs to happen here in a few years. So thanks. I'm grateful to be asked to speak today.
Okay, very good. Thank you, Rich. Really interesting. Yes, biological and physical science is very important to what we're doing in the future. And just a note to our audience that we will be taking your questions towards the end. And I do hope someone asks about squid research. So reminds me of my favorite Disney character from Despicable Me, Vector, who has a squid launcher. So Rich, if you all are working on a squid launcher, I'd like to be the first to know about it. Okay, next up we have Josh Brost. Josh, over to you.
All right. Thank you, Trudy. It's very good to be back at Humans to Mars. I'm always excited to come speak here, and it's great to be on a panel with others that are like-minded and trying to solve problems that really will enable Mars to be possible. About relativity specifically, we were specifically founded to really solve a subset of those problems to make a permanent presence on Mars possible. And beyond that, to make life interplanetary. At the outset, we realized that for Mars really to happen, it can't be just 1, 2, even 10 companies working on it. We need dozens, if not hundreds of different companies out there solving different parts of the problem set to build an ecosystem that really makes it sustainable. And so again, it's great to see the other panelists speaking here today. If you look at what we're doing at Relativity that's unique, we're really focused on developing the industrial base for Mars with a real specific focus on making it possible to manufacture very large scale, high performance systems. So if you think about it, there's multiple different phases that in the process of taking us to Mars. Right now, we're kind of in the research and explore phase where we're sending autonomous systems to Mars to get kind of ground truth and some initial scientific information. That'll be followed by human exploration, where you send people for missions where they're going and doing initial research. And in those missions, they can take everything that they need to do their missions with them. But to make the flip from exploration to settlement and a permanent presence, you need to develop an industrial base that makes it possible to make everything you need once you're there. You can't rely on supply ships coming every 26 months to give you resupplies when something breaks. You can't afford to have dozens of spares for every possible system. And so it really becomes critical that you develop a capability to autonomously manufacture what you need when you're there. We also realized as a company that all of the technical problems you need to solve to make a Mars manufacturing system possible can also be used to make better products on Earth. So if you think about it, what do you need? What are the traits for a system needed to make manufacturing on Mars possible? First, it has to be autonomous. It can't rely on human intervention. It needs to be incredibly reliable. You can't be reliant on sending people there to fix it. It needs to be part of your critical infrastructure. And so it needs to really operate flawlessly and be able to self-correct. On top of that, you need it to be very power and materials efficient. On Mars, we're not going to have a huge excess of power anytime early on, and any feedstock that we send or that we manufacture on the surface will be very precious resources that need to be used efficiently. And then finally, it needs to be incredibly flexible. The whole goal is to be able to manufacture things on site or in situ that you didn't know you needed before you departed for your mission. If you look at each one of these things being rolled into a manufacturing platform on Earth, it also leads to building the ability to manufacture products that are less expensive, that are more reliable, and that can evolve very, very quickly, leading to a great commercial opportunity here on Earth as well. As we start moving forward with our technology, we're initially deploying it on Earth to manufacture launch vehicles. We're starting with a small launch vehicle that's intended to enter service at the beginning of next year. We're following it with a larger, fully reusable launch system that's due to enter service in 2024. And in this development process, we're already demonstrating the flexibility of our platform by manufacturing early hardware for our next generation launch vehicle that's 5 meters in diameter, using the same factory that we're using to build our initial smaller launch vehicle that's just over 2 meters in diameter. So I'm excited to be part of this panel. Look forward to the questions and look forward to seeing what the rest of the panelists have to say. And again, thanks for inviting us to be here.
Okay, Josh, excellent. Thank you very much. And yeah, there's not going to be a store on every corner, so you're going to have to make what you need when you don't even know you need it yet. Okay, very good. Next up, we have Pascal Rosenfeld. And like I said earlier, he is with Aleph Farms. It is not often that you have the word farms in the title of a company that's associated with the aerospace industry. So without giving too much of that away, Pascal, over to you, please.
Thank you very much. Thank you for the invitation to this panel with amazing companies. And again, it's very inspirational. So I'll start with a quick introduction. Aleph Farms is an Israeli company. We are about 50 now, mostly biologists. And what we do for a living, we cultivate high quality meat cuts directly from the cells we isolate from healthy animals, without killing any animal nor polluting the environment. So our purpose and our mission is to build resilient and sustainable food systems for tomorrow. What we like to say is that we want to deliver the tastiest and healthiest meat experience to anyone and anywhere. And this includes obviously our planet Earth and Moon and the Mars. So next slide, please. So to put this into perspective, I'd like to illustrate our key milestones to date. So the first one is that Aleph was the first company to cultivate real beefsteak from stem cells, meaning not just fiber muscles, but the full structured steak. Then Aleph was the first company to cultivate meat in space. We'll talk about this later. And lately, 6 months ago, we're the first to 3D bioprint a whole muscle ribeye steak that you can see on the right, looking delicious. So we think of space as our laboratory, or more likely like a Formula One racing team, where we're testing new technologies in extreme environments to test a new frontier. And we definitely think that space will allow us to build better systems for Earth, and that will benefit to all of us here on Earth. So to build near zero resources systems and improve nutrition for all. And next slide, please. So to tell you a little bit more about the origin of 3D bioprinting and origin of the company, it's very important to underline that our technology is stemming from medical research initially, and the expertise of Aleph co-founder Professor Shulamit Levenberg, whom you can see on the left side of the picture. She's running the Levenberg lab at the Technion Institute of Technology, which is our MIT in Israel. And she received numerous international prizes, and her work is at the convergence of stem cells, tissue engineering, and 3D bioprinting, which is of interest to us today. So the Levenberg lab is a leading testbed for human tissues and reconstruction. And what they do is that they develop tissue to regenerate or repair injured heart muscles, for instance, or spinal cords, or other types of muscles like abdominal muscles. And they also develop vessel networks, in fact, to perfuse inside the tissue. So we're really talking about 3D structured tissues. So all this exceptional IP from the medical world and 3D tissues was transferred to Aleph Farms a bit more than 4 years ago to focus on meat production. And the ensuing technology allowed us to produce many different types of cells. So this translates into what you've seen on the picture, which means it's a fresh beef 3D whole cut steak that incorporates all the natural elements that you would see in a normal steak, because it's pretty much mimicking nature, and it delivers pretty much the same. So in February 2021, we announced this World 3D bioprinting of a ribeye steak, and this new collaboration allows us to make thicker, fattier steaks, and maybe in the future to build it more specifically on demand. So how does it work? This bioprinting, we just the process begins with the 3D bioprinting of living cow cells, and then the cells are incubated so that they can grow, differentiate, and then they interact, which is very key. So they interact so that they can reach the texture, the 3D texture and qualities of a real steak. So it's pretty much a natural development in the 3 dimensions. So again, it's not a 2D layer lasagna. It's really a full 3D printed steak. So the result is that you get the same muscle, fat, and let's say organoleptic and flavors as you would get at your favorite butchers. Next slide, please, about the ISS experiment. So this was 2 years ago exactly, pretty much today. And with our partners at 3D Bioprinting Solutions in Moscow, we were the first to cultivate meat biofabrication on the ISS. And what we did is that they took our cells and they grew it. So the technology that they use is what they called magnetic levitation in a controlled magnetic field in order to work with microgravity. And this method opens opportunities for assembly of organs and tissues without the need of a scaffold. So this is quite a shift. And so this technology is called, they call it formative printing. And this allows faster printing and higher safety. And next slide, please, about 3D printing now on Mars. To answer a few questions already. So what we think it can bring, the first thing you can think of is obviously fresh food. So we want to deliver something that is delicious and let's say that you want to eat. And the main problem is that what we are shipping to the ISS or to the Moon or Mars tomorrow, in order to be made shelf stable, is highly processed, like very, very processed. And in the end, it loses a lot of its properties, characteristics, and acceptability by the crew. And in the end, what happens is that they eat less, which is not good for productivity and even for their psychology and balance. And in addition, the packaged food that we're sending to Mars, and as George said earlier, we cannot wait for resupply, wait for the next 6 months, is that the packaged food is the nutrients inside decay with time, and a solution would be to produce fresh food, meaning using thawed cells that we would on demand revive and grow in an incubator. The second thing is that we can build complex meat structures and with different adjustments of the fat and the muscle parts and the proteins and so on. The third thing that is very, very interesting is that it would liberate the creative food design, meaning that if you think in 3D, you can imagine high customizations in shapes, in texture, and this is the more likely the fun part that would be interesting for, let's say, Mars dwellers. And you can think of fat marbling, colors, or repartition of the different vitamins and taste and flavors and so on. The second element I would like to discuss is safety and security, food security. So it's a core question on Earth, but it will be also on the Moon and on Mars. So our processes allow no pathogens and no contamination, which is key for space. And the 3D bioprinting processes will be vacuum sealed. So this is a controlled environment without any food security issues in mind. And the last thing is that it's really low footprint. So when you think about living on another planet and you have limited resources, you better use them sparingly. So the first thing is that it's on demand. So again, you have a cryo tank, cryopreservation of cells, and you pick up pretty much the species, the breed that you want, and you put it in a bioreactor. It grows for 2-3 weeks, and then it's ready for the menu. And so if you just revive only what you need, it means that you're saving on supply chain inefficiencies, packaging, and so on. And the last element is really waste reduction. So one element is that shelf life for meat is between 3, 4, 5 days in a supermarket. And the fact that we don't have any biological activity on our meats, there's no pathogens, means that the shelf life is largely extended, which is very precious for, let's say, trips from here to Mars or on Mars, specifically less waste and so on. So these are the major benefits of 3D bioprinting on Mars for let's say, meat and food supply that I could think of for the moment.
Okay, very good. Very, very good, Pascal. Thank you. Listen, that ribeye is going to have some seasoning, so salt and pepper, all that good stuff. You need to over season a steak usually. So, but it does look appealing, like you said, and It probably helps your cause that we're right before lunchtime, making everyone hungry. But in all seriousness, very thought-provoking. I don't deal with this aspect of exploration at all, and human sustainment. So it's fascinating stuff. Thank you. All right, and then finally, Justin Coogler. Justin, Redwire has been in the news a lot lately and recently on Wall Street. So there's a lot of exciting things going on at your company. So if you would provide us your overview and take it from here.
Happy to do that, Trudy. Thank you. If we could go ahead and pull up the slides. All right, thank you. We do a lot of different things at Redwire with the 7 companies that we've acquired since we were incorporated last year. And what I'm going to talk about today is the work that we've been doing at Mission Solutions, inherited from Made in Space, to take advantage of technology developments today that will lead to Earth independence tomorrow. Next slide. So really at Redwire, our focus is on accelerating humanity's expansion into space by delivering reliable, economical, and sustainable infrastructure for future generations. In our view, that takes the form of 3 different sectors. One is the general robotic OSAM technologies that Trudy mentioned before. Our flagship effort there is called Archinaut 1, or if you're talking NASA budget line items, we call that OSAM 2. And that is the first satellite that will manufacture and assemble parts of itself after it's launched. And we think that's critical for taking advantage of the more affordable, more sustainable launch opportunities that companies like Josh's are developing, to actually turn space itself into an industrial park where we can build large-scale solar power systems, where we can build large-scale radio frequency antennas, and even space telescopes that go far beyond what's physically possible. We say that we're breaking the tyranny of the launch shroud. The second area is what we call microgravity industrialization. So it's actually putting the microgravity environment to work for terrestrial benefit. Examples of that include our first-in-class Z-Blade manufacturing facility that we flew to the space station 4 times in less than 18 months, which I think has to be some kind of record for doing manufacturing operations on board the space station, as well as ongoing work that we're doing with NASA and the LEO commercialization team on identifying new industrial processes that would benefit from scalable access to microgravity. But what we want to talk about with y'all today is what we call exploration manufacturing. So that's taking advantage of advances in situ manufacturing, whether that's 3D printing or even other methods, to make it so that we can really live off the land on planetary destinations, and so that we can solve the next generation of Apollo 13 style problems on deep space transit vehicles, but do so in a way that is more affordable and more sustainable, just because it's not physically possible to carry every possible tool, every possible repair that we could ever imagine. Instead, we want to make that a digital system so that we can generate better solutions on the fly. Next. The first example of that is our Vulcan technology. We've been developing that in partnership with the in-space manufacturing team at NASA Marshall, as well as the Lunar Surface Innovations team and NASA STMD for a couple of years now. And we're working towards a first flight demonstration. This combines both additive and subtractive manufacturing of metals and polymers, so that we can generate actual flight critical quality parts in situ with relatively simple and well characterized feedstocks. And as you can see from the pictures, this is not your standard either vapor deposition or power bed fusion methods, because those kinds of materials are extremely challenging, if not dangerous, to manage in a microgravity environment. Instead, we use metal deposition processes to create what we call the near net shape, so that we can get the density and bulk material properties that we need. And then we've developed subtractive miniaturized methods with built-in catchments so that we can generate those high quality, high surface precision surface features that you need for things like high RPM turbo machinery parts, as well as high temperature items for things like human life support systems and other high performance systems in human rated vehicles. And in this example, we used the lab prototype to actually machine out the NASA meatball. This is important because as we develop the in situ resource capabilities that Trudy mentioned earlier, we can use those feedstock streams for local materials and local manufacturing, thus reducing the total amount of material that has to be transported out of the Earth gravity well and to those future destinations. Next. The next step in our development is what we call the mobile end effector laser device. This is a welding system that's designed to be used both on the end of robotic arms as well as handheld tools to enable us to do in situ welding, assembly, and manufacturing using essentially space modified versions of terrestrial advances in laser welding technology. This particular approach we think is promising because not only can you do kind of spot welding of existing structures, you can also incorporate wire-based feedstock so that you can do a combination welding and metal additive process. You can see some examples of that in the pictures here on the right sample. You can see where we've used the additive welding process to patch a hole in a stainless steel plate. Next. One of our ongoing projects that we actually have on board the space station right now, which I'm very excited about, is using a combination of regolith as a bulk aggregate material with different kinds of binders so that you can use it for bulk additive construction. We're doing it at small scale with a specialized print head in our ISS additive manufacturing facility right now as proof of concept. But we've also done lab scale demonstrations where we've been able to make things like adapter cones for external hoses and equipment, shells to cover inflatable pressurized modules to provide debris and radiation protection, as well as structural test articles. Moving ahead, we think that this is could be a very critical capability for building permanent infrastructure on the moon and on Mars, because literally all that's required once we validate this technology is the delivery of the manufacturing unit on site. And in some ways, this is actually easier from a sustainability perspective on Mars, because not only do you have the bulk soils that are available to you, we also have through the permafrost readily available sources of water and the atmosphere carbon dioxide. So we can use the exact same ISRU processing technologies that other folks that are working with STMD are doing to create the binders that we would need to make this truly self-encapsulating. And that's important both in terms of making sure that this is a low energy process as compared with say, for example, centering methods, but also it provides safety for any human interactions, because you capture any of the jagged fines, and you can prevent toxic materials like perchlorates from leaking out because of this self-sealing, self-encapsulating nature. Next. We've also been looking at how we can actually use bricks for local construction. Very similarly, using combinations of bulk aggregate materials and polymer binders. You can either make it a polymer encased design, where really you're just using the aggregate as filler. For example, you may want to use that on the inside of a pressurized surface, as well as a mixed aggregate for things like landing pads, finished surfaces for rovers and equipment garages, and we've been looking at how you can dramatically reduce the amount of binder through those methods, so that, for example, you could use these things in flame trenches for large scale landers on the Moon and Mars. Next. In the near term, we think it's important to demonstrate these capabilities affordably and at smaller scale on precursor missions before they get fed forward into the critical path. Most recently, we worked on this concept called the lunar manufacturing demonstration for NASA's tipping point, where taking the same lessons that we've learned from doing small scale process demonstrations on the ISS, being able to do the same thing on future CLPS landers for technologies like surface welding, regolith and polymer blending, as well as adapting some of the work that's being done in the offshore oil and gas exploration industry to manufacture and produce basalt fiber for aspects where we need good tension in the structure, but we also need high thermal resistance. And again, based on lessons that we've learned from operating on the ISS, we designed these demonstrations to be easy for crew and robots both to operate. So, for example, any one of these small-scale demonstrations could be incorporated as a mission kit on future autonomous vehicles, or operated by surface crews with handheld devices. So, these are the kinds of things that we're looking at Redwire to prepare for this amazing future of sustainable Artemis surface missions, and then feeding forward to that Earth independence that we'll need on Mars.
Okay, very good. Thank you, Justin. A lot of content there. A lot of diverse things going on for Redwire. So let's see, it looks like we might have about 12 or 15 minutes left. We might have to do somewhat of a speed round of questions. There is a lot of interest that the four of you just generated. So we are going to start. I'm going to start with Pascal first. Two questions from our audience I'd like to ask. First of all, will it be efficient to 3D print food on Mars in the early 2030s or in 2030? And if you have the answer to this, how much beef can you actually make on Mars based on, say, a single cow cell? What's the quantity? So people want to know the quantity. How does that translate?
Okay. So the first answer is I don't know whether we'll be on Mars at this date, but it sure is accelerating. The pace is accelerating, so maybe it will be the case. And will it be viable? this is what we're working on. So I definitely hope so. And the process how it works. So we take a cell. All the cells developed at Aleph farms are non-GMO. So this is very important for us. And the second thing is that they are non-immortalized. So we take the cell and then we just build a cell line. And then from that cell line, it's, I won't say it's unlimited, the quantity of beef or whatever mammal or other species that you can develop. But given the right environment and the right nutrients, this is unlimited. We just revive the cell that is frozen, and then we grow it on demand.
Okay, very good. And just quickly, if you could talk about terrestrial applications. How about bioprinting being used on Earth? Especially, you talked about food insecurity. So what about that?
So as I said earlier, we think of space as a Formula One testing, or more likely a lab in let's say intense weathering, intense environment. And the application are very obvious for us. We are focusing for Earth's application on automation, miniaturization, and everything linked to recyclability. So the purpose is really linked to 3D printing in general. It's to use the least possible amount of any inputs to produce the maximum possible rations of food. So it's the feed to food ratio, actually.
Okay. All right. And as expected, people are usually concerned about food and housing. So Josh, could you talk about that a little bit? There have been a couple questions from the audience about habitats, 3D printed habitats, and plans for Mars housing. So can you address that a little bit?
Sure. So if I think about all of the different problems that need to be solved to make Mars really possible, large-scale infrastructure is definitely a core part of that. And so, if you think about needing to make habitats that can survive really long durations, be really resilient to any kind of damage, something that starts with a metallic liner probably makes some sense there. I think there's likely a combination of regolith and metallic solutions there that will ultimately make that possible. But that's only one part of the problem set. Like, to make life possible there, you need some large facilities to store oxygen, to store water, to store propellants. You need to have like true infrastructure, piping, connecting different things, like all that kind of basic infrastructure we take for granted on Earth. You sit at your home and you've got a connection to the water at the street and the sewer line at the street. That's all stuff you need to figure out a way to manufacture there. On top of that, you start looking at surface mobility. You may be able to take parts of that surface mobility system with you for initial missions, but to build large surface mobility platforms over time in situ, you also will need the ability to produce large, strong, and simple structures. And I think the metallic printing is a key part of that solution space.
So just a quick follow-up to that. Why aren't there more products that are 3D printed on Earth today?
I think there are a bunch of reasons, kind of all coalescing at the same time. I think first, 3D printing is still really a nascent technology, and you see a lot of companies are doing kind of R&D demos with them, but there are very few companies who fully embraced it in a way in which it drives their whole development team to learn to take advantage of the benefits of 3D printing. With that said, I would say there also was an investment problem, but if you look at over just the last few years, the amount of investment capital flowing into 3D printing companies, it's massive. You're talking billions of dollars over just the last few years. The one segment that we would say is still underserved is the really large scale 3D printing. There's huge amounts of money going into kind of the powder bed printers or other technologies that produce things that would sit on your desktop, but there are very few other companies working on the really large scale capabilities that allow you to print an entire airframe or an entire propellant tank or an entire major pieces of infrastructure. But I think you are seeing more adoption, and if you look at the growth over the last few years, that it's kind of an exponential curve. And we're one of the companies that's trying to really accelerate that development even faster.
Okay, very good. So Rich, I'd like to pull you into this part of the conversation. So could you talk a little bit about how 3D printing technologies can be used, both on the way to Mars and then on the surface?
Right. So our two main technologies that we're working on, I can speak maybe a little more specifically about that. So the bioprinter, which we call our BFF, our biofabrication facility. Space, we've got to have good, cool mission patches and acronyms, right? So I think we've got a winner with BFF. So the bioprinter, and then the Fab Lab, so the 3D metal printer. We're going to be, just like a lot of these technologies are tested, right? We go to low Earth orbit microgravity, where we can do some testing, we can work things out. We've printed some human knee menisci on board the station, and that's helped us learn what improvements we might want to make for that. And the Fab Lab 3D metal printer will launch, I'm sure after Justin's, probably in, I think, 2024 timeline. And we're going to learn how to what we can do with it and how to operate it better in low Earth orbit, and then maybe on the Gateway. I think the Fab Lab is intended to be tested aboard the Gateway, surface of the moon, deep space transport on the way. We found that 3D printing right now aboard the station, because of all the transfers of the signal when you make a command to operate it. I don't know how it's been for you, Justin. For us, it's 6-7 second delay sometimes, depending upon which satellite it connects. And working those things out now while we can, sort of in this cradle, this incubator of technology aboard the ISS has been super helpful. And so I think once we learn how to optimize these technologies for remote use and optimize them to be super useful by crew members out of low Earth orbit, I think we'll see it deployed on that deep space transport of some sort, where you can, with metal printing and electronics printing, sustain. I think somebody mentioned the Apollo 13 moment, and probably Justin as well. So we want to help provide tools that provide solutions for the what ifs once they get there. And again, the bioprinter could be a way for helping with restoration of immune systems for deep space crews. Food source, again, right now we're making our bioprinter available to anybody that wants to use it. I mean, we're certainly using it for our own programs, but any company or any researcher that wants to use BFF right now in space, they can. And then once we get to the surface, again, I think some of these technologies that have been super useful in 1/6 gravity and in 0 gravity will be useful on the surface of Mars as well. Printing electronic assemblies, making metal parts that will that powder bed capability be as effective in a 0.38 Gs? I'm not sure. I think our solution will work in any part of that spectrum, any part of that continuum of gravity. And again, bioprinting on the surface of Mars, I think, could be helpful for sustaining human health, injuries, living bandages, things like that, as well as a food source. So that's what gets us excited about the possibilities of being a part of moving into deep space.
Very good. So by offering that up, you risk your BFF becoming someone else's BFF. I'm just going to point that out.
I know there is that risk, but we're happy that it could be useful to whom.
Yeah. No, that's good. That's very generous. Okay. There are definitely two more questions I want to try to get to in the essence of time. But Justin, while you were speaking, someone asked a very practical question I'd like to throw over to you is, who does parts inspection? Is it done robotically? Do you inspect it terrestrially and then trust that remotely? How does that work? Can you address that?
Yeah, that's a great question, and that builds on work that we've been doing with ISS operations, as well as the development of the OCM2 mission. We are developing and building into the system a lot of those kind of in situ, checking and process monitoring systems, so that way we can verify that the feedstock that's coming in meets the quality standards, that the manufacturing operation is proceeding the way it's supposed to, and then that the output product is what it's supposed to be, because we are literally building things for customers that they will never see them with their own two eyes, which is a wholesale change from the way that things have traditionally been done in aerospace manufacturing and product development. And so we are spending a lot of time developing those, in situ V&V technologies and algorithms, so that it's just baked into the process.
Can you touch on real quickly what the difference would be with manufacturing on Mars to say what's being done on ISS now, just some basic differences?
So it's interesting in that in many ways, the ISS is a resource constrained environment. We have limited amounts of power, limited amounts of volume, even limited amounts of crew time. And so even though Mars is so much further away and so much more challenging in some respects, it's also a resource-rich environment with all the local resources and materials, and the kinds of power systems that are going to be required to sustain human life and grow those missions. The technologies that we're working on fit well within those envelopes. And so I think it's how, like on Antarctica, the mindset changed from an expeditionary mindset to having essentially an industrial park at McMurdo that supports a permanent research station at the South Pole. We've got to have that same kind of mindset for establishing permanent infrastructure on the moon and then eventually on Mars to sustain those missions, because we can't just FedEx everything that we need to those explorers and to those people living and working on those planetary bodies. They've got to have that critical infrastructure that Josh talked about, so that it does become a sustainable human presence and not just a temporary expedition.
Okay, very good. This might be the last question based on time, but Pascal, I want to ask you. So we've kind of given you, a little bit of a hard time, not a hard time, but just talk about like steaks and food and stuff like that. But I really would like to hear about the other applications, such as medicine and health, which clearly are at play here. So could you address that? And you're still muted.
That was a trick. So what we can imagine in a few words is personalized nutrition. So that health and dietary needs, they vary from one person to another and from season to season, actually. So we could customize each meal according to one's needs at a given moment. The second thing for space is definitely morale and psychology, because food is about fun, is about bonding and so on. It's very natural for mammals and humans. And let's forget about this freeze-drying food and pre-packaged food, and let's imagine that we could on Mars or on the Moon prepare our own food together. So the reality is that cooking, pretty much like gardening, are the basic hobbies of all humans. This is our favorite pastime. So we'll have plenty of time while we're on Mars or on the Moon. So why not let's say, concentrate on this aspect? And the last one is regenerative medicine. As I said earlier, our technology is stemming from the medical field. And if we can 3D print from stem cells cultivated meat, then potentially one day we can help grow organs, which can come in handy when you're like 6 months away from the next supply.
Yeah, exactly. I'll just say cooking is not my favorite pastime, but anyway. So, okay. Well, listen, thank you all very much. We could spend an hour just with each of you individually. We really could. There's so much content here. Thank you to each of you for being here, to our panelists. Thank you to the audience for your thoughtful questions. I apologize we could not get to all of them. I know when we prep for panels like this, we think we're going to have all the time in the world, and the next thing you look down and time is up. So I hope you enjoyed the panel today. I hope you enjoy the rest of the Humans to Mars 2021 Summit, and hope to see you all at the next time we get together to talk about topics like this. So that's it for us today. Thank you.
Thank you very much.
Thank you, Trudy.
Thanks, everyone.